Good morning to all. I am Dr. Thayalan from Radiologic Physics Foundation, Chennai. Last week we have been discussing about the principle of radiation detection. Today we are going to talk about radiation detectors, especially ionization chamber. What is ionization? Ionization is the removal of electron from neutral atom. So the ionization chamber is based on the principle of ionization effect. That means when radiation passes through a medium, it does ionization in the medium. The medium can be a gas medium or solid medium. Example for gas medium is xenon gas. Example for solid medium is semiconductor detectors. When ionization takes place, it creates positive and negative ions we simply called ion pairs. These ion pairs can be collected by applying an electric field so that one can measure the current as well as charge in the system. So let us consider the figure. So this is actually the ionization chamber principle. This is the chamber volume which is filled with a gas. Now radiation is passing through the medium. It does ionization and produces negative and positive ions. Consider that the electrode is given a positive potential and this electrode is given a negative potential through an ammeter. This electrode is called anode, the other electrode is called cathode. Because of the electric potential, the negative ion move towards the anode and positive ion move towards the cathode. They constitute a current in the circuit which can be measured. The measured current is proportional to the radiation intensity. This is the basic principle of the ionization detector. So this is another format of the diagram in which you can see that this is the active volume of the ionization chamber. The central one is called anode. It is connected through the circuit through a ammeter. This is actually the outer electrode is called cathode. Generally it is in the cylindrical form. So the net objective here is the total charge collector is proportional to radiation intensity. That means if higher the radiation intensity, higher the charge collection in the active volume. If lower the radiation intensity, lower the charge collector in the active volume. Let us discuss about the air equivalent wall. Ionization chamber generally used to measure X and gamma rays in Röntgen. We all know that Röntgen is defined in air. Then what will happen? Thicker air wall is required. How to reduce the wall thickness? So instead of air, one can also use solid wall. In that case, there are two conditions to be satisfied. The solid wall material should have same absorption and scattering characteristic of air. This is one condition. The other condition is the effective atomic number of the wall material, solid material, should be equal to effective atomic number of the air. If these conditions are satisfied, then the wall material is called air equivalent wall. So let us consider the figure. The first figure actually you have the cavity in which the ionization takes place. This is surrounded by a air. You can see this is the thickness of the air wall. To reduce the air wall, we can also do like that. We can put air equivalent material and this is the cavity. The air equivalent material is made up of solid which have same absorption and scattering characteristics of air, and the effective atomic number of the solid wall material is equivalent to the effective atomic number of the air. If that is the case, what will happen? Once you have the air equivalent wall, the wall thickness is reduced. This is the advantages of using the air equivalent wall. Once you make a air equivalent wall, you can make a chamber like this. So this is the central electrode, this is the insulator, this is the wall material. If you make a chamber with air equivalent wall material, then it is called a thimble chamber. The wall is called thimble wall. So another important condition is the wall thickness. The wall thickness should be greater than the range of maximum energy of the secondary electron. That means we should not allow the electron to escape from the active volume, for which this is the condition to be satisfied. The wall thickness should be greater than the range of maximum energy of the secondary electron. Once we have a air equivalent wall, what we can achieve is, we can achieve electronic or charged particle equilibrium. What is that? If we have a charged particle equilibrium, the number of electrons leaving the volume is equal to number of electrons emitted by the wall entering the volume. So this is the advantages of having a air equivalent wall. So another thing is, the chamber becomes energy independent. That means chamber can be used for any radiation energy for measurement. What are the optimal wall materials we have? Graphite, bakelite and Teflon are the suitable wall material which can satisfy the previous condition we discussed. The doubt comes whether the wall material thickness is same or not. The wall material thickness varies with the energy, radiation energy. Higher the radiation energy, higher the wall thickness, lower the radiation energy, lower the wall thickness. Let us discuss about the chamber gas and volume. The chamber can be filled with any type of gas. The only condition, it is free from dead time losses. That means when radiation interaction takes place from first to second interaction, the chamber should not take additional time to record the event. So therefore you look for always gases which are free from dead time losses. So what is the gas available such gases? High Z gas such as argon with atomic number 18 and xenon atomic number 54 are suitable gas mediums to be used in ionized chambers. The collection volume varies. It may be from 0.1 cc to 1.0 cc. So what we collect is, we collect the charge per interaction we collect, and operating voltage of the chamber is around 50 to 300 volts DC potential. The chamber may be a sealed one or unsealed one. The unsealed one is generally referred as vented type ion chamber. What are the special features of the ionization chamber? The ionization chamber can be used either current mode or integrated mode. It can be designed with a different shape, size and gas. It suits different clinical demands. That means it can be used for radiotherapy or nuclear medicine or diagnostic radiology. The only limitation is, it cannot be used to count individual radiation events. So what are the type of ionization chamber we come across in our field? The first one is free air ionization chamber. This chamber is not used in hospital, but it is available in secondary standard laboratories. It is used for calibration purposes of dosimeters. The second one is farmer chamber. Generally it is having 0.6 cc, generally used for radiotherapy for calibration. You can see the structure of the anatomy of the farmer chamber. The chamber is having an active volume like this, blue color, sensitive volume. This volume only 0.6 cc. It is surrounded by a cap. It is called a thimble cap with air equivalent wall material. And here is the aluminum stem. This is the central electrode. The blue one is central electrode. And then this is fitted with the insulator here. And also the guard ring. You know that actually the why guard ring is used in this system. So commercially it is available like that. This is the cable part, this is a stem part, this is the chamber part, this sensitive volume. This is the volume to be exposed in the radiation field. So what are the voltages we operate in radiotherapy? Around 200 to 400 volts DC we operate in radiotherapy. The volume we operate radiotherapy is 0.6 cc to 0.015 cc. This very small field we use it, like pinpoint chambers. What is the current we can measure? From 6 picoamperes to 6 nanoamperes we can measure. The dose rate 0.1 to 10 gray per minute we can measure with this. So this is the farmer chamber, commercial chamber with build-up cap. used in radiotherapy application for cobalt as well as the linear accelerator. Apart from that, we do have semi-flux and rigid chambers with a volume of 0.125 and 0.3 cc. This is especially used for 3D dosimetry. The next one is pinpoint chambers. They are available with a volume of 0.015 cc, 0.03 cc and 0.016 cc, especially used for small field dosimetry in IMRT treatment like that. The next one is plane parallel chamber or extrapolation chamber. This chamber is available commercially as marker chamber or rose chamber. They are used particularly in electron dosimetry or skin dose measurements in patients. The next one is well type or re-entrant ionization chamber. It is used in brachytherapy for source calibration. The next one is isotope calibrator used in nuclear medicine for calibrating the radiopharmaceutical. Using this, one can find out the activity of the radiopharmaceutical or radionuclide which is available in the hospital. The next one is monitor unit ion chambers. This is used in linear accelerators. And then CT xenon gas detectors. See, olden days CT detectors are made with xenon gas detectors. Nowadays they are replaced with solid state detectors. Then pencil type ion chambers are used in CT scan for quality assurance. They are used with the phantom for CT dose index measurements. The next one is dose area product meter, which is called DAP meter, used in cath lab and CM equipment like that. The other one is packet dosimeter used for personal monitoring, and then survey meter made up of pressurized ion chambers. So this is the semi-flux ion chamber having a volume of 0.3 cc, and this is used in water phantom measurements, RFA, radiation field analyzer. We use this type of chambers. The other one is pinpoint ionization chamber having a 0.03 cc with a diameter of 2.9 mm. This is used in small field dosimetry, especially when we go field sizes less than 5 by 5. We use this type of meters, especially for precision radiotherapy. This is a parallel plate ionization chamber which is having a thin entrance. When radiation passes through, there is no much attenuation of radiation takes place here. That's why it is very much useful for skin dose measurement in patients. This is commercially available in the form of marker chamber or rose chamber. So this is used for electron dosimetry as well as the skin dose measurements in the patient. So this is the type of monitor chamber used in linear accelerator for monitor unit calculation. So left side is well type ionization chamber used in brachytherapy for new source calibration. The right side is isotope calibrator used in nuclear medicine for radionuclide calibration, especially in gamma camera or in PET CT. This is commonly used. This is the group of xenon gas detectors used in CT scan. The left side is a xenon gas detector. There is a group of xenon gas chambers. It is arranged in a focused fashion. Olden days it is used as a main detector in the CT scan. Nowadays this is replaced with solid state detectors. Now the right side one is a pencil type chamber used to CTDA measurement with a phantom in a CT scan. So this is a dose area product meter attached to cath lab. It will measure dose rate and area. So in a particular area of the patient, how much dose is delivered is given in, say, a dose area product. So this is the packet dosimeter works on the ionization principle. This is used for personal monitoring. So nowadays it is available in the digital format. So both analog and digital type is available with a different dose range. This is a pressurized survey meter used for radiation survey in a linear accelerator setup. I hope you enjoyed the video. Kindly subscribe and succeed. Thank you very much for this. We will meet in the next lecture with a new topic.